Okay, let's take a look at a different kind of plot now called stem plots, or sometimes called stem and leaf plots. So here's some data of 20 female AP Stat students who were asked the question, how many pairs of shoes do you have? And asked to represent this data with a stem plot. So as you can see here, we have some females who pairs of shoes everywhere from a low of 13 up to a high of, looks like 57 is a high. I don't know what girl that is that has 57 pairs of shoes, but okay, we will accept that data. So the first thing we're going to do is we're going to figure out what our stems are. So as I mentioned, we had a low of 13 up to a high of 57. So it kind of makes sense that we break stems up into tens. So all the tens, all the 20s, 30s, 40s, and 50s. So these are the stems. We put a line there and we start putting down our leaves. And kind of just in order. So the first number was 50. So I put that number 0 right there, and that's the 50. And then 26 was there, and then there was another 26, etc., etc. It's helpful, though, to go ahead and take this data and organize it. And I'll be honest with you, a lot of you will skip this step when you make a stem plot and go right to this step by just making sure you put the numbers in order as you write them down. But as you notice here, they're in order. So like here we have 3 different 13s, plus a 15 and a 19 in the 10 stem. And then 22, 2 23s, 24, and 2 26s, and the 20 stems, etc. But they're in order from smallest to biggest. And so if you're organized, you can skip that middle step and go right to this. Again, as I mentioned before, it's really important to have a key here to represent, to tell the reader exactly what the numbers represent. In this case, 4-9 represents 49. You can pick any example in there just to show that that's what the numbers represent. Okay? So this is a stem or stem and leaf plot. Now let's take a look at the data, and we're going to add in the males. So we're going to add in 20 males who were asked the same questions. As you can see, their range of values is a lot different than the females. For whatever reasons, the males don't have as many shoes as the females do. And we noticed when we did the females that a lot of the data was bunched up, that it was kind of hard to see any patterns because there was so much data in each of the tens group. So sometimes it's to our benefit to kind of split up the data, split up the stems. And so I'm going to try to show here what that would look like. So if I bring up the data here, I'm going to split the stems, instead of by groups of 10, I'm going to make them groups of 5. So this first stem would be from 0 to 4. This next one would go from 5 to 9. The next stem would go from 10 to 14. So if you notice, I'm breaking up into groups of 5. Okay? And I'm going to do this. I'm going to put the males on the right side and the females on the left side. So if you notice here, I took the male data and put it on the right side. Again, all the 0s to 4s here in the first stem, the 5s to 9s in the second stem, the 10 to 14 in the third stem, etc. And I did the same thing with the females, but I put the females on the left side. So it was very important to put some labels here to know which side is which. And again, representing the key. Okay? So this is how you make a stem and leaf plot. In this case, this is a back-to-back stem and leaf plot, because you're actually comparing males and females. And I can see already there's a lot of difference here. The males are bunched around the low end of the numbers, between, say, 0 and 15 or so, where the females seem to be bunched around about 10 to almost 40. You can see that most of the data is there. So we can see some big differences here. But when we split up the stems and we actually make a back-to-back, put the females on one side and the males on the other. Okay, the next type of graph that you need to look at, that we have looked at already, is box plots, but now we're going to look at what's called a modified box plot. And basically, modified box plots are a way to represent outliers. So if you notice here, these two boxes here represent outliers. The other numbers are the min, the quartiles, Q1 and Q3, the median, and the maximum. Okay, it's the same numbers. Remember, this is the maximum that's not considered an outlier. Okay, so this is the key to, and we're going to look at the data here. This is Barry Bonds. He was a fairly prolific home run hitter who played mostly for the San Francisco Giants, although early on he did play for the Pittsburgh Pirates. And this is his home run totals, ranked in order from his fewest number in any given year to his highest number. If you look here, all the numbers seem fairly reasonable, and so you get up to the very end and you look at, wow, 73 was considerably higher than anything he did any other season. Okay? And so this looks like it might possibly be an outlier. So In order to make our box plot, we have to determine the 5-number summary. The minimum here is 16, so we put this at 16. The maximum, well, is 73, but again, that could be an outlier, so we want to take a look at this. Q1 turns out to be at 25. Okay. The median is at 34. Let's look at the lines there. They kind of break them up into groups. And Q3, remember, is halfway between 40 and 42. So this actually is 41. And so to determine whether 73 is an outlier or not, remember, I got to go Q3 minus Q1. So 41 minus 25, which is 16. I'll multiply that by 1.5. That comes out to be 24. I'm going to add that to Q3. So 41, 24 plus 41 gives me 65. So this turns out to be the boundary that determines whether outliers exist or not. So in this case, 73 is an outlier. So my maximum then becomes the biggest number that's not an outlier, which is 49. We actually only have one outlier in this set, and it would be at 73. Okay? And so that's what a modified box plot is. The only difference is that the modified box plot actually shows outliers, where box plots would not. If you use it to 83, 84, we always pick modified box plots. I'll show that to you later on, how to get that. The Inspire, thankfully, only does modified box plots, so we don't have to worry about that. It doesn't even do box plots anyways. So once again, I could actually compare Barry Bonds totals to, say, Hank Aaron, who was another prolific home run hitter who played back in the 60s. He played for mostly the Atlanta Braves, although I do believe he played for a couple other teams also. But this would be what is considered a side-by-side box plot, showing it's vertical, showing the difference between Bonds and Aaron's. And you can see, for example, that Bonds had a greater range. You can see as low as just below 20, all the way up to that 73, where Aaron is a little more consistent. And he had, while he did have a low, was around 15. His high was only about 45. Okay, and Barry Bonds was famous for breaking Hank Aaron's career home run record. Hank Aaron had hit the most home runs in the history of baseball until Barry Bonds came along and broke it. Okay, but here down below is box plots that are side by side, but notice they're horizontal. This first one is not modified, because you notice here it doesn't reflect the outlier. It just goes to the maximum irregardless. For the most part, we do not look at these kind because that's the main reason we look at box plots, is to determine outliers. So this would be a better box plot because if you notice here, it shows that outlier. This is the one for Barry Bonds where they hit 73 home runs, which was considerably greater than all the other ones. But these are two different types. We call them side-by-side box plots, and they're great for comparison purposes. When you want to compare one factor to another, it's important that you make sure the scales are the same, and etc. Okay? So these are different types of plots, both stem plots and box plots. Again, I hope you've seen both of these before in previous courses.